And the superposition principle says exactly that. It says exactly that if y1 and y2 are solutions to a linear equation, to a linear homogeneous ODE, in fact, it can be of higher order too, although I won't stress that. In other words, you don't have to stop with the second derivative. You could add a third derivative and fourth derivative, as long as the form remained the same. Then that implies automatically that C1y1 plus C2y2 is a solution. Now, the way to do that nicely is to take a little detour and talk a little bit about linear operators. And since we're going to be using these for the rest of the term, this is the natural place for you to learn a little bit about what they are. So I'm going to do it. Ultimately, I'm aimed at a proof of this statement, but there are going to be certain side excursions I have to make. The first thing, side excursion, is to write the differential equation in a different way. So I'm going to just write its transformations. The first, I'll simply recopy it, what you know it to be. Qy equals 0. That's the first form. The second form, I'm going to replace this by the differentiation operator. So I'm going to write this as d squared y. That means differentiate it twice. D it and then d it again. This one I only have to differentiate once, so I'll write that as p dy. P times the derivative of y. The last one isn't differentiated at all. I just recopy it. Now, I'm going to formally factor out the y. So this I'm going to turn into d squared plus pd plus q. Now, everybody reads this as times y equals 0. But what it means is this guy, it means this is shorthand for that. I'm not multiplying. I'm multiplying q times y, but I'm not multiplying d times y. I'm applying d to y. Nonetheless, the notation suggests this is very suggestive of that, and this in turn implies that. That's what I'm just transforming it. And now I'll take the final step. I'm going to view this thing in parentheses as a guy all by itself, a linear operator. This is a linear operator called a linear operator. And I'm going to simply abbreviate it by the letter L. And so the final version of this equation, it's been reduced to nothing but Ly equals 0. Now, what's L? You can think of L as, well, formally, L you would write as d squared plus pd plus q. But you can think of L, the way to think of it is as a black box. A function, what goes into this black box? Well, if this were a function box, what would go in would be a number, and what would come out would be a number. But it's not that kind of a black box. It's an operator box, and therefore what goes in is a function of x, and what comes out is another function of x. The result of applying this operator to that. So from this point of view, differential equations, trying to solve the differential equation means you want what should come out, you want to come out 0, and the question is what should you put in? That's what means solving differential equations in an inverse problem. The easy thing is to put in a function and see what comes out. You just calculate. The hard thing is to ask, you say, I want such and such a thing to come out, for example, 0, what should I put in? That's a difficult question. And that's what we're spending the term answering. Now, the key thing about this is that this is a linear operator. And what that means is that it behaves in a certain way with respect to functions. The easiest way to say it is, I like to make two laws of it. That L of u1, if you have two functions, I'm not going to put in the parentheses x because that You know, it just makes things look longer and not any clearer, actually. What does L do to the sum of two functions? If it's a linear operator, it must, if you put in the sum of two functions, what you must get out is the corresponding L's, the sum of the corresponding L's of each. So that's a law. And the other law, linearity law, and this goes for anything in mathematics and its applications, which is called linear. Basically, anything is linear if it does the following thing to functions or numbers or whatever. L, the other one is of a constant times any function, I don't have to give it a number now because I'm only using one of them, should be equal to C times L of U. So here C is a constant, and here, of course, the U is a function. Functions of X. These are the two laws of linearity. An operator is linear if it satisfies these two laws. Now, for example, the differentiation operator is such an operator. D is linear. Why? Well, because of the very first things you verify when you, after you learn what the derivative is, because the derivative of, well, I won't write it in the D form, I'll write it in the form in which you know it. It would be D applied to U1 plus U2. How does one write that in ordinary calculus? Well, like that. Or maybe you write D by dx out front. Let's write it this way, is equal to U1 prime plus U2 prime. That's a law. You prove it when you first study what a derivative is. It's a property of, from our point of view, it's a property of the differentiation operator. It has this property. The D of U1 plus U2 is D of U1 plus DU2. And it also has the property that CU prime, you can pull out the constant, that's not affected by the differentiation. So these two familiar laws from the beginning of calculus say in our language that D is a linear operator. What about the multiplication law? That's even more important, that U1 times U2 prime. I have nothing whatever to say about that here. In this context, it's an important law, but it's not important with respect to this study of linearity. So there's an example. Here's a more complicated one that I'm claiming is a linear operator. And since I don't want to have to work in this lecture, the work is left to you. So the prove that L is linear. All right, where are we? Well, all that was a prelude to proving this simple theorem, the superposition principle. So finally, what's the proof? Well, the proof of the superposition principle, if you believe that the operator is linear, then L of C1, in other words, the ODE is L. L is D squared plus PD plus Q. So the ODE is Ly equals 0. And what am I being asked to prove? I'm being asked to prove that if Y1 and Y2 are solutions, then so is that thing. By the way, that's called a linear combination. Put that in your notes. Maybe I better write it even on the board because it's something people say all the time without realizing they haven't defined it. This is called a linear combination. This expression is called a linear combination of Y1 and Y2. It means that particular sum with constant coefficients. Okay, so the ODE is Ly equals 0, and I'm trying to prove that fact about it, that if Y1 and Y2 are solutions, so is a linear combination of them. So the proof then, I start with apply L to C1Y1 plus C2Y2. Now, because this operator is linear, it takes the sum of two functions into the corresponding sum of what the operator would be. So it would be L of C1Y1 plus L of C2Y2 That's because L is a linear operator. But I don't have to stop there. Because L is a linear operator, I can pull the C out front. So it's C1 L of Y1 plus C2 L of Y2. Now where I'm trying to prove that this is 0. Well, what is L of Y1? At this point, I use the fact that Y1 is a solution. Because it's a solution, this is 0. That's what it means to solve that differential equation. It means when you apply the linear operator L to the function, you get 0. In the same way, this is y2 is a solution, so that's 0, and the sum of 0, C1 times 0 plus C2 times 0 is 0. That's the argument. Now, you could make the same argument just by plugging C1 y1 plus plugging it into the equation and calculating and calculating and calculating, grouping the terms and so on and so forth. But that's just calculation. It doesn't show you why it's so. Why it's so is because the operator, this differential equation, is expressed as a linear operator applied to y is 0. And the only properties that are really being used is the fact that this operator is linear. That's the key point. L is linear. It's a linear operator.